Hello folks, and welcome back to Femboy Mathematics. So today's video is going to be concerning group theory. So this was requested by a viewer on this channel, or our subscriber called Sad Girl. And yeah, that's what we're going to be doing for this extras episode. Now the next episode will come soon, trust me. And I think that's when we're gonna officially go to calculus. So I'm sorry for this long wait. I've been more focused on my Professor Femi channel. So yeah, really sorry about not uploading much on this video. And if you guys did catch me in Coscarny during Sunday, yeah, I was there wearing a maid outfit. I practically destroyed my dignity, but I still remain somewhat sane from that event. So okay, so today we're going to be talking about group theory and what exactly groups are. So the definition of a group is rather abstract. Here's the thing with groups. It's rather abstract and it'll require some prerequisites in order to understand this lecture. So the one prerequisite, of course, is set theory. So the notion of objects or collection of objects, okay? But I will still give you guys the bare minimum to understand the theory. So group theory is the study or a mathematical branch that studies a certain mathematical object called a group. So group is not what you guys would usually think in real life, you know, like groups of people, stuff like that. There's a separate term for that, which is called a set, which is a collection of things, right? Or mathematical objects. So throughout the entirety of your mathematical journey, if you carry on over to collegiate level studies in mathematics, you guys will encounter these things called sets, and inevitably you guys will. Or these things called mathematical objects. So mathematical object is anything that we can do math with, basically. And an example of a mathematical object is a function, you know, f of x equals y, you know, that machine. There's also a map, which is a more general form of a function. There's a morphism, which is a much more general version of the map. There's of course the set, a collection of objects. That in itself is an object, or mathematical object. There's also, of course, nothing. Nothing is also an object somehow. I know you can debate on whether that makes sense or not, but in mathematics, we're not here much to philosophize, but more or less just do math. And numbers, of course, themselves are mathematical objects because we can do math over them. What else? Limits, stuff like that, are all mathematical objects. And an important thing to note before anything else ensues, before I discuss more advanced topics, mathematics is not real, okay? It's never real, it never has been real. There's no such thing as mathematics is embedded in nature or stuff like that. I know you guys can debate on that, or you guys can call me wrong on that, but personally speaking, from all of the stuff I've done in mathematics, it doesn't exist. All mathematics is a nice and neat logical model of things around us, okay? So the number 1 is not a real thing. It's not a real thing, it's more of a concept, okay? It's a number that is a concept or a collection of all things that are 1, basically, or maybe even the count of it, if that makes sense. Okay, so going back to group theory, so what exactly is a group? So first we need to go back to the notion of a set and functions. So, more general version of a function is called a map. Okay, so what exactly is a map? So map is not exactly what you guys think. If I have two collections of objects, which I'll call A and B, I'm pretty sure you guys have seen this diagram back in high school or in elementary, if your, of course, school has taught topics advanced that early, of course, you'll notice this diagram. So we have a bunch of arrows going from this set onto this set. And these arrows are called maps, or all of them is called a map. And there are 3 main types of maps out there. And I'm not talking about the disgusting people on Twitter, okay? Not those maps. What I mean by map here is we have 3 types. Okay, so it's a correspondence between 2 sets. So the first type of map is called a bijection, and it is what you guys are familiar with, the function. The function is a special case of a map. And it is such that the size of both these sets, which is basically how many elements are inside them. Elements are the formal name we give to things that are inside the set, okay? So basically the size of these two sets are practically the same. They have the exact same amount of elements inside them. And for every element inside A, there is a distinct element inside B. So that's a bijection. An injection this time is one wherein the size of one of these elements is bigger than the other. So in this case, B is bigger than A. So we end up corresponding elements onto some elements here, but not all elements here. So it's like, say, it's 3, but there's an additional 4th element that nothing in A gets mapped onto, or nothing in A gets mapped onto, yeah. So that's an injection. So think of it this way: if I have a syringe, right, and you're getting your vaccine or something like that, or you're gonna have like some medicine injected into you. Think of it that way. So you have small quantity getting put inside your body, which is big, right? So you have many things inside you, and then little things inside. That's what's called an injection. At least that's how I intuitively understand it. Now I know there are more formal definitions for these things, but I'm just giving you guys the intuitive spiel of it all. And the last one is called a surjection. So basically this time A is bigger than B, okay? And so that means there are a few elements in B and a lot of elements in A, and so there is going to be some case wherein elements overlap in case of in terms of what element they get mapped onto. And what I mean by get mapped onto, I know you guys probably don't understand, is basically what element they essentially are in the other set. Okay, so if I take an element over here and I put it through the map, which is still a machine technically, I have another element, or I get another element. It gives me another element that's inside B. Okay, and what I'm so that element I put in the map gets mapped onto that output I get. All right. So yeah, one is that the sizes of both sets are the same. One is wherein one is bigger than the other, and another one's when another one is, of course, smaller than the other. Okay, so that's a map, and of course we denote it by this way: F takes A into B. All right, so it's still a machine. Okay, it's still a machine that you can still think of it as a machine that takes in stuff inside A and gives us stuff inside B. Okay. All right, so yeah. Next thing up on the agenda of this video to lead up to is called operators. So there are many definitions for what exactly an operator is, especially when you're in physics. Femboy physics, shout out to you. I know you will probably say that that is not what an operator is, but there really are an arbitrary amount of definitions out there for operators, so shrug. So an operator, basically, it's just a map, but it's sort of more well-defined or more specifically defined. So operator. So there are 3 types, or actually infinite amount of operators, or infinite types of operators. So the first one is called a unary operator. And this is what you guys are very familiar with. It's the function f of x. It takes in one input and gives us one output. I put x inside f and get y. That's called a unary operator. An example of this would be, I suppose, a function, but more specifically in terms of arithmetic. So in reality, not only are operators like basically functions, right? Another terming for functions, but rather they are sort of a formalization, right? A more rigorous definition for what arithmetic is, okay? So first is unary, we take in one input and give one output. So if x here is part of big X and y is part of big part of x, still part of x, and say that f maps x onto itself, right? Or rather, that's the operator. F is the operator here. So next is binary. So this is f maps x onto itself. Next is a binary one, which takes in two inputs this time. So I have an f, x, y, and gives me a z. So this is denoted via this here, f maps x cross x, and takes it onto x. Okay. So going back to our definition of a map, we want to read this thing as f takes stuff inside x and takes them to stuff inside x, or the other set. Okay. So this time I have two inputs. That's a binary operator. And what this symbol over here means, x cross x, is another thing in math called a Cartesian product. So if I have a set A and another set B, the Cartesian product between A and B is another set. Okay, A cross B, which is defined to be all ordered pairs. A, B, such that A is inside big A and B is inside big B. And this symbol over here, this small e here that you guys see in high school and stuff like that, is basically our notation for set membership. And what we mean by that is this small b, which can be anything you can think of. It could be a number, it can be an object, stuff like that, is inside B. So it's an element of B. So it's inside B. There. So a Cartesian product. So it gives me pairs of numbers. So think in terms of, okay, if a regular line, right, of points is just, just numbers themselves, right? If you can think of numbers as the line, right? A Cartesian product of that line with itself gives us a plane or an XY axis. And then, it's basically all possible coordinates on that. Okay, that's one way of interpreting a Cartesian product. Or in fact, that's the best way of interpreting the Cartesian product. Okay, so yeah. Takes in two inputs, which is basically here. So you notice this notation here. These two notations are equivalent. So it takes two inputs in x and gives me an output in x. Next is a trinary, which is f of x, y, and z, and gives me an element t. So this is denoted f of x times x onto x. And you guys can probably generalize it from there. It can range to n inputs, and gives me one output. That's called an NRE operator. Okay. So an example of a binary operator, which is the most common one, and in fact what we're going to be discussing in the definition of a group, is addition. So addition takes in two inputs, let's say 1 plus 2, and then gives me an output which is 3. So there, that's an example of a binary operator. Now we can define addition or multiplication as a trinary operator. Like say 1 plus 2 plus 3 gives me 5, right? But we can sort of degrade the trinary definition into a binary definition. So I just take sort of the function or the operator of another smaller operator between two elements, and that basically gives me the trinary definition. Trinary operator definition. Okay, so I'm gonna write a dot here to say or tell you guys that it can generalize further. I know I'm sort of beating around the bush right now, and saying, oh well, you haven't even gotten into the definition of what a group is yet. Well, the thing is, in pure mathematics, I shit you not, it's gonna get very abstract. Okay. The best way you can understand these things is through their rigorous definitions. I mean, it's not bad to give images and sort of mental constructs, but there will be no real appreciation if we don't show them the rigor of it all. So I'm sorry if this video has been somewhat very abstract and boring thus far. So let's get to the actual notion of a group. So in group theory, well, notably in groups, what our plan is to codify or formalize the notion of symmetry and things like that. So what do I mean by symmetry? Okay, so if I have a stick and then I poke it through the middle of the top of this rectangle here, and then I rotate it 360 degrees and get the same thing, that's a symmetry. A symmetry is basically any action that I can do on an object, or whatever I can do on an object, that makes it look the same. Likewise, if I take a stick and put it into the middle of this rectangle and rotate it 360 degrees, or 180 degrees, still 180 degrees is good enough, it gives me a symmetry. It's a symmetry. Or if I do it 180 degrees. still a symmetry. Don't mind the writing here. Still symmetry. It still looks exactly the same if it's blank, okay? And likewise, if it's in this position, and then I do a 180-degree rotation around this pin here, or this stick I put through here, it's a symmetry. That's a symmetry. Likewise, I can reflect it 360 degrees, and it's a symmetry. Now, if you guys don't mind the yellow padding here, if you think this is white or exactly the same as this part, yeah, 180-degree rotation is still a symmetry. Okay? So symmetries are basically actions or movements I can do on the object that makes it look exactly the same. Now how about translation? Like, okay, it's in this position and in that I switch to that position. That doesn't matter because when we're just talking about the object itself, we're not thinking of them as part of some space that we can define or move it around. It's just inside a void. Think of it that way. If I'm talking about, say, a space or an object, a shape, just think of it in some blank space. It's not part of a coordinate system, it's not part of an axis or stuff like that. It's just out in the void. That's the best way of thinking of mathematical objects abstractly, okay? Well, that is until you define them to be on a coordinate plane. Okay, so we're gonna go straight into the formal definition of a group, and this will be a bit heavy. Okay, so a group, which I will denote as G, is a set A with a binary operator, which I will call circle or circ, that takes A cross A and takes it to A, such that, okay, there are three main rules that a group or this operator must satisfy in order for A with this to be considered a group. So first thing is that, okay, one, for all, so this upside down A means for all, so any element inside A, it must hold, okay? For all A, B, C inside A circ B circ C is the same as A circ B circ C. So I do the operation on B, C first, and then apply A, apply that resulting thing to A is the same as this thing. And yeah, so second, for all A inside big A, there exists, so this inverted E means there exists, right? So it's literally what I'm saying it is. There must be another element, okay? Or there exists, not really must be, but there is another element, which I call E, such that A circ E is the same as E circ A, which is just A. So I have an element such that if I apply the operator on that element and our given element A, it just leaves A. It doesn't do anything, essentially. And three, for all A inside big A, there exists an A to the minus 1, called an inverse of A, such that A circ A to the minus 1 is E. It's the same as A to the minus 1 circ A. Okay, so I know you guys think this is a bunch of garble, but I will explain it later. So last requirement. Oh wait, no, that's not a real requirement. Okay. So there are only three main axioms. The fourth one that I was about to mention is a specific type of group. Okay, called an abelian group. Okay. So what do I mean by the first one? I already explained a while ago, so I'm gonna move to the second one. The second one means I have another element, a very special element inside A, such that when I put it into this machine that takes into inputs, right? And I have another element inside A, and I put it into that machine with that special element, it only gives me that one element. So an example of E over here, not Euler's number, not at all. An example of E here is 0, and that's under addition. So the operator's addition, and I have 0. So notice that if I add any number to 0, it just gives me that number. Nothing happens to that number. So that's why 0 is called that. And 0 is technically E in this case. And we call E the neutral element or the identity element. The reason why it's called an identity is because you know, it's just the identity. Like if I try to do something, or if I ask it to interact with another element, it just leaves that element with the same identity. So think of it like I guess a boyfriend that doesn't change at all, right? So yeah, that's E here. And of course, the third requirement is that there is another special element, a polar opposite. You can think of it as polar opposite. A polar opposite of an element A, such that if I put these two into the machine or our operator, it gives me the identity element. Okay, so an example of an inverse, so this a to the minus 1 is called an inverse of A. An example of a to the minus 1 is, I suppose, negative numbers, right? So if I have addition and I have the integers, which is basically all whole numbers that are both negative and positive, no fractions, of course. If I have 1, or let's use a different example. Let's say 3, okay, 3. The inverse of 3, in the case of addition, is negative 3. Because if I add 3 and negative 3, I just subtract them both, I get 0, which is the identity element, according to addition. Because the thing is, if various operations have different identity elements, like in multiplication, the identity is 1. Okay, and inverse is of course a reciprocal, so it's a fraction, 1 over that thing. So I'm not going to discuss multiplication just yet now. Okay, so yeah, what I'm basically saying here is that if I do something to my object, say I rotate it like this, and then I rotate it again or some other way, it's the same as doing the second rotation and doing the first rotation. Okay, and then the second one here, there is an action that does nothing. So I'm just doing nothing to this. That exists inside the set of all stuff I can do to this, okay? For example, of course. And then the third one is that if I do a rotation here, like this, say I rotate it like this, there is another element, there's another element inside the collection of all possible things I can do on this, such that if I do this, and then I do that next rotation, I end up doing nothing. So, okay, that would be, if you could guess it, doing this, right? So I'm doing this. So I'm gonna rotate it like this, and I'm gonna do that second thing I said, which is do this. And you notice that it looks exactly like I didn't do anything to it. So that's exactly, or that's a visual way of explaining the third rule, right? So this is a group, very abstract. And the way we denote it is via this ordered pair. So this is not like elements, you know, like coordinates. This is one way of saying A is equipped with this operator. So what I mean by equipped is that any element in A can be put into this machine, basically. So think of it like a building, right? So I have a building, say a house or a building basically, and the people inside it are the elements of that set. So the building is the set, the people are inside it, and the operator basically, or the operation on that, or what we call the group operation, is basically the house rules. What the house rules, yeah, what the people inside it can do amongst each other. So they can interchange, like mingle around, stuff like that, and rules for whatever that. Yeah, so these are rules basically. So we can think of this operator as a rule instead of a machine, or other apart from a machine, of course. So we say that A with this operation circ is G. So this is a notation here. Right. So what is an example of a group? Alright, so an example of a group is the integers. So the integers, basically speaking, is all whole numbers. So this is one way of writing out a set using the braces, okay? So negative infinity up to positive infinity, but not infinity themselves. Those aren't objects, those are just basically what I mean by it goes on and on forever. And then so it's like minus 2, minus 1, 0, 1, 2, and dot dot dot, off to infinity. Positive infinity, of course. So, what if I equip this with addition operator? So, this that takes z cross z and gives me another integer z. And of course, you're supposed to define the operator. Okay, if I just say, okay, it's this, so addition is this, it's something we call a not well-defined thing. What I mean by well-defined is that basically you answer all possible questions that anyone can ask you about it. Say, okay, yeah, you did say it's a map that takes two inputs and gives another input inside Z, but what does it do? What exactly does it do to the elements? And you're like, yeah, that's what I mean by it's not well defined. So let's make it well defined. So for an A, B inside Z, so integers, for all A, B inside Z, the addition of these two things, so the function of these two, gives A plus B. So we just add A and B according to our usual notions of addition, which is derived from piano arithmetic, which I will not discuss in this video because, frankly, just studying the foundations of mathematics will make you go insane. Okay. All right. So yeah. So A plus B. So that's our definition. And so now it's well-defined, somewhat well-defined, because if they ask me, okay, yeah, it does A plus B, but what's our range, or what's the function that it operates over? I say that it operates over the integers. Takes two integers and then spits out an integer, right? It's like, oh, so yeah. Okay, so the reason why Z here is a group, so I'm declaring Z and this addition is a group. Not only that, I will show that it is a special type of group called an abelian group. Okay. So first thing you guys want to notice is that, okay, I have an identity over here. I have 0, such that if I add it to any of these numbers, I'm going to put 0 here and 1 here. That's 0 plus 1, which is just 1. So I have an identity. So it satisfies already the second axiom or second rule of all groups. Okay, so third one, okay, I have 1 here, say for example 1. I have an inverse. I have an inverse here such that if I add 1 and negative 1, that's just 1 minus 1. So 1 plus minus 1 is just 1 minus 1, gives me the identity, which is 0. So third rule is satisfied. And that applies for any of these integers. It's any whole number and their negative counterpart, basically. So say, like, you may be thinking, I didn't place it here, but 5 is an element of the integers here. And so is negative 5. And the same thing happens if I try to add them two together. They give me 0. Okay. All right. And so the first rule, I know it's a bit hard to see here right now, but 1 plus 2 plus 3 is the same as 1 plus 2 plus 3, but I add 2 and 3 first. So 1 plus 2 gives me 3, and then I add 3 into it. I add 3 to that. That gives me 6. The same thing happens when I add 2 and 3, which gives me 5, and add 1, which gives me 6. Same thing. So it satisfies all those possible things. And another important thing is closure, of course. So I take two inputs, 1 and 2, say for example, I put them into this machine and let it do its thing, gives me 1 plus 2 is 3. 3 is an integer, so therefore it's closed. I mean, I know that this is just an intuitive way of proving it. There's a more formal way of proving that this here's a group via piano arithmetic once more. Okay, so this is an example of a group. Another example of a group is a triangle, an equilateral triangle. So what I mean by equilateral is that it has sides that have the same length. Okay, so what's one symmetry you guys can think of that can leaves this thing unchanged? So basically, another version of a group, or another interpretation of a group, or a type of group, is one called a symmetry group, which basically contains all symmetries as its elements. So instead of numbers, it contains symmetries of an object. So one symmetry you can think of course, is along this one here. I just flip this over, it looks exactly the same. Likewise, along here, I flip it, here I flip it. So this is one symmetry. And then there's another symmetry here, and then a symmetry here. If I flip along these lines, I flip the figure along these lines, it looks exactly the same. Another symmetry is if I put a pin here in this center, and I rotate it, so 170 degrees, all right, 170 degrees. not radians, in degrees. If I rotate it 170 degrees, it gives me the exact same thing. If I rotate it 360 degrees, it does the same thing. In fact, if I compose that 170 with another 170, it gives me 360. So it's essentially, we have essentially done nothing. Alright? And of course, with each of these flips along these lines, there is a corresponding anti-flip that does nothing to it. So if I'm going to label these vertices as 1, 2, and 3, if I flip along this line here, it permutes 1 and 2. So 2 goes here, 1 goes here, right? There's another move, right? Such that if I apply it on, that new triangle, it gives me, or puts us back where we started, right? So that makes sense. So S, I'll call it S, and it contains, let's call this A, B, and C, these symmetries. So what I mean by A is flip along this line. Alright? And next there is rotate by 170 degrees and rotate by 360 degrees. Wherein this is just the do nothing, or E in this case. How about A to the minus 1? A to the minus 1, let's put A to the minus 1, B to the minus 1, and then C to the minus 1, which is basically the inverse. And of course, just assume that R170 and R360 inverse are the same thing. But it doesn't matter if the identity element has an inverse. It already is the identity, so it is its own inverse. Okay. So, reason why this is a group with composition. So, composition. So, circ is one way of generalizing the notion of an operator. So, it could be a stand-in for anything. But in this case here, we're saying it's, okay, I'm going to do one of these guys, and I'm going to do another one of them in sequence. That's what I mean by this. So, yeah. Let's say I rotate along A first. So I perform A. So 1 and 2 gets flipped, and then I perform B. So I do this, and then I do this. So this time, 2 goes to 1, 1 goes to 3, and 3 goes to 2. It's the same thing as rotating by 170 degrees. It's the same thing as doing that, right? Because we essentially move each of these guys. We move them. So it's close. That satisfies the first one. The second one, yeah, of course, I established these guys have inverses, so it already satisfies that. It has R360 degrees, so I rotate along this marker now, 360 degrees, and it leaves me with nothing. I've done nothing to the triangle, essentially. So that's our identity. So I have an identity now. If I apply 360 degrees here, and I apply, say, A, it does nothing to A, essentially. I mean, these two rotations are independent of each other. So if I do, let's do one wherein they depend on each other. So R170 and then apply 360. So I do 170 degree rotation. It permutes 1 and 3 and 1 and 3 and 2 and 1, basically. Okay. So it rotates it like this. And then I do the 360 degree rotation. So it does nothing to it. It leaves us at that state wherein we rotated it by 170 degrees. So there. So this, with this, in an order pair is a group. So S and composition is a group. That's a group. So that's the basics of group theory. And actually, going back to our example with the integers and addition. So these two over here. This is also called this is also known in the business as an abelian group, or it's called an abelian group. I know some of you are gonna pronounce it as abelian or abelian or whatever. I would like to pronounce this abelian. Okay. So what I mean by abelian group, it's named after Abel. I think he was a mathematician. What they mean by abelian is that, okay, so right now our addition operator, which is a plus b, right now we can't claim that this is the same as if I flipped it together. For all I know, it could give me a different element as if I did a plus b. So what I mean by here is that you guys will notice that 1 plus 2 is the same as 2 plus 1, or any other number, or any whole number, or any integer basically. It gives us the same result. if we flip these two together. Because right now, the reason why we call this an ordered pair is because we know, like, because that's one way of saying A comes before B. So it's always A plus B and not B plus A. That would be this over here, BA, which is B plus A. So B comes first. But the thing is, addition here with the integers is an abelian group. And what I mean by that, I know, I keep beating around the bush. What I mean by that is that these are the same. These are the same. So AB is the same as the addition of B plus A. So A plus B is equal to B plus A. And that's evident. 1 plus 2 is equal to 2 plus 1, which are both resulting to 3. Likewise with 5 and 6. So 5 plus 6 is the same as 6 plus 5, which gives us 11. Same thing. Same exact thing. So that's an abelian group. Of course, an example of a group that most groups are not abelian. Okay, there are groups that are abelian, especially this and the real numbers. But there are certain groups that are not abelian, such as let's say for example SO2. So this is a group. It's called the special orthogonal group of order 2. I know that sounds scary, but what I basically mean here, the most intuitive notion of this is basically rotations of the 3 coordinate axes or 2 coordinates axes. So this is Y, this is X. So SO2 is the set of all possible things we can do, rotations we can do on here. So maybe rotate like that, like that. Okay, and these are expressed in terms of matrices. And oh man, in my linear algebra basics, I have not discussed matrices yet, and I'm starting to sort of regret that because this is a group of matrices in reality. Okay, so I guess you guys can just read up on that. All right, there are many of intuitive ways of imagining what a matrix is. All right, so the determinant of all these matrices is 1. All right, so yeah, so all possible rotations we can do over here. So if we imagine there's a square here, basically, that's one way of thinking about it. We can embed a square in this space, right? And SO2 is all possible rotations we can do on the square. And you'll notice that if I mark these edges right, specifically, if I rotate these things and then if I do one operation, do another one, it's not the same. Okay, it's not the same. So if I rotate it, likewise with, let's say that this eraser is inside the space wherein SO2 operates on. Okay, so if I rotate it this way, all right, and I rotate it, say this way, it's different. So it goes like that. So we rotate it. It's different from doing the second one and the first one. So like this and then like that. Different. It looks entirely different as if I did this and then this, right? That's what I mean by non-abelian group. So order does matter. So in this case, for any AB inside SO2 or any non-abelian group, A plus B is not equal to A minus B. B plus A, sorry. Or, because the thing is, SO2 is with an, implies an composition, which is matrix multiplication. So this time A and B are matrices, not numbers or symmetries. So A cert B is not the same as B cert A. Because multiplication of matrices is non-commutative. I mean, addition is commutative, but not multiplication of matrices. So this is the basics of group theory. I know we've sort of extended to past 39 minutes, but this is the best I can condense group theory into, I mean the basics of it. So yeah, I guess expect more videos in the future in this very uncomfortable position. But I guess it's the setup we have to work with for the time being. So I guess just bear with me on this one, and especially with the more abstract lectures to come, bear with me on those. So yeah, I will do the exact same outro with Professor Femi, which is, this is a good place to stop.